Hello, welcome back. In this video, we'll discuss the Planck's radiation law. This law was proposed by Max Planck in 1900. The foundation for the Planck's radiation law is the failure of Rayleigh-Jean's law to explain the ultraviolet catastrophe. Please recall that the Rayleigh-Jean's law predicts infinitely large energy density in the UV region, which is contrary to the blackbody radiation spectrum. The infinitely large amount of energy densities in the UV that were estimated using the theoretical model suggested by Rayleigh-Jeans indicated some of the shortcomings of the classical theories. The main important aspect of the Rayleigh-Jeans law is it is founded on the principle of equipartition of energy. The Rayleigh-Jeans law uses the Boltzmann principle of equipartition of energy, which states that each harmonic oscillator will have an energy that is equal to kT, where K is the Boltzmann's constant and T is the temperature of the blackbody. Max Planck realized that this component of equipartition of energy is giving rise to the infinitely large energy densities in the UV region. Max Planck put forward a revolutionary postulate that an oscillating atom can absorb or re-emit energy only in quantities that are integral multiples of h nu. The revolutionary postulate of Max Planck is that an oscillating atom can absorb or re-emit energy only in quantities that are integral multiples of h nu, where h is the Planck's constant and nu is the frequency of the oscillator. So this is the revolutionary postulate that was put forward by Max Planck to explain the blackbody radiation, and all other values of energy are forbidden. And this individual discrete unit of energy h nu is called energy quantum. This assumption allows the Planck's radiation law to be derived basing on energies of the molecular or atomic oscillators must be quantized This principle in general gives us the possible values of the energy of the oscillators of frequency nu or E is equal to nh nu, where n is the quantum number, h is the Planck's constant, nu is the frequency of oscillation. N can take integers 1, 2, 3, 4, so on and so forth, and h is the Planck's constant, whose value is numerically equal to 6.626 into 10 power minus 34 joule second. So emission or absorption of radiation could take place by a discrete amount of energy h nu. Atomic oscillators can exist in a discrete state of energies which starts from 0, h nu, 2 h nu, 3 h nu, so on and so forth. Since we are talking about a very large number of atomic oscillators in a black body, we cannot address the atomic oscillators individually. So we may have to adopt a statistical approach. The statistical approach that we adopt here is the Maxwell-Boltzmann distribution. N is equal to n0 exponential minus En upon kT, where En is equal to nh nu and n0 is the number of oscillators in ground state, that is E is equal to 0. This can be written as n is equal to n0 exponential minus nh nu by kT. This is called the Maxwell-Boltzmann distribution function. We make use of Maxwell-Boltzmann distribution function to obtain the average energy of the oscillators. To obtain the average energy of the oscillators, we consider n number of oscillators in a system in thermal equilibrium at temperature T. Then one can write N, that is the number of oscillators with energy En, as N is equal to n exponential minus En upon kT. This is from the Maxwell-Boltzmann distribution. Since the energies of the oscillators, they assume discrete values, we have to sum over all possible oscillator states to determine the average energy. We represent the average energy. The average energy of the oscillators is represented with an E in rectangular braces. Average energy one can obtain by taking sum over all possible oscillator states and divide it by the total number of oscillators. So we can write the average energy E as sigma n is equal to 0 to infinity En Nn upon sigma n is equal to 0 to infinity Nn. The numerator gives us the total energy of all the oscillators and the denominator gives us the number of oscillators. Thereby we get the average energy. So this can be written as sigma n is equal to 0 to infinity En n exponential minus En by kT upon sigma n is equal to 0 to infinity n exponential minus En by kT. We are substituting this value here and this becomes the average energy E is now can be written as sigma n is equal to 0 to infinity En exponential minus En by kT upon sigma n is equal to 0 to infinity exponential minus En upon kT. The capital N is taken as common, so one can write the average energy in this fashion. But we know that En is equal to nh nu. This expression can be rewritten as average energy E is equal to sigma n is equal to 0 to infinity nh nu exponential minus nh nu upon kT divided by sigma n is equal to 0 to infinity exponential minus nh nu upon kT. This can be expanded as average energy E is equal to, we shall substitute n is equal to 0 here. So when n is equal to 0 is substituted, we get a 0 for the first term. The second term will be for n is equal to 1. So we get h nu exponential minus h nu by kT plus 2h nu exponential minus 2h nu by kT plus so on and so forth. When n is equal to 0, e power 0 is 1. So we get 1 plus exponential minus h nu by kT plus exponential minus 2h nu by kT plus so on and so forth. In this expression, we write by substituting exponential minus h nu by kT with x. This expression becomes average energy E is equal to h nu x into 1 plus 2x plus 3x square plus so on and so forth upon 1 plus x square plus so on and so forth. The numerator is a progression that can be written as h nu x into 1 minus x whole power minus 2. Since the denominator is a progression that can be expressed as 1 minus x to the power minus 1, we can write this as h nu x upon 1 minus x, which can be written as h nu exponential minus h nu by kT upon 1 minus exponential minus h nu by kT. This can be rewritten as by multiplying numerator and denominator with exponential h nu by kT. We can write this as h nu into exponential minus h nu by kT into exponential h nu by kT divided by 1 minus exponential minus h nu by kT into exponential h nu by kT. This gives us the average energy as h nu by exponential h nu upon kT minus 1. Say this is A. Now we shall recollect the assumptions that were used in the Rayleigh-Jeans law. The Rayleigh-Jeans law uses the Boltzmann's principle of equipartition of energy, which is equal to kT. Whereas here we are getting an average energy that is equal to h nu upon exponential h nu upon kT minus 1, which means the principle of equipartition of energy is not applicable in the microscopic world. Means the Boltzmann's principle of equipartition of energy, which gives us the average energy of the oscillators as kT, holds good only in the macroscopic world. Now we write the number of oscillators in the frequency range nu and nu plus d nu, which are estimated to be the number of oscillators between nu and nu plus d nu are estimated as 8 pi nu square d nu upon c cube. By multiplying the average energy with the number of oscillators within the range of nu plus d nu, one can obtain the energy density of the blackbody radiation. By multiplying this with the average energy of the oscillators, Planck obtained the energy density in blackbody radiation. So energy density in blackbody radiation is E nu is equal to 8 pi h nu cube by nu square by c cube into 1 over exponential h nu by kT minus 1. Similarly, when you write c is equal to nu lambda, one can write this expression as E lambda is equal to 8 pi hc upon lambda power 5 into 1 over exponential hc by lambda kT minus 1. These two expressions are known as Planck's radiation law. The first one is in terms of the frequency of the oscillator. The second one is in terms of the wavelength of the electromagnetic radiation. The second expression, essentially, it completely fits into the blackbody radiation spectrum. Therefore, the Planck's hypothesis of quantization of energy is a valid statement. It has revolutionized the modern physics. In this video, we have stated that Max Planck has put forward a revolutionary postulate to explain the blackbody radiation in 1900. The revolutionary postulate of Max Planck is that an oscillating atom can absorb or re-emit energy only in integral multiples of h nu, and all other values of energy are forbidden. The individual discrete units of energy is called as energy quantas. The Planck's law is based on the principle that the energies of molecular or atomic oscillators must be quantized. It is said that energy E is equal to nh nu, where n is the quantum number that can take values n is equal to 1, 2, 3, 4, so on and so forth, and h is the Planck's constant. So we have said that atomic oscillators can exist in a set of discrete energy states that can be given by 0, h nu, 2 h nu, 3 h nu, so on and so forth. We have said that one cannot handle each atomic oscillator individually, so we adopt a statistical approach. The statistical approach adopted is Maxwell's Boltzmann distribution, which states that nn is equal to n0 exponential minus en upon kT, where en is equal to nh nu. We have used the Maxwell-Boltzmann distribution in the current context, where nn is n0 exponential minus nh nu upon kT. We have used this to obtain the average energy as a summation of the energies of all the oscillators, which can be written as sigma n is equal to 0 to infinity en nn upon sigma n is equal to 0 to infinity nn. After doing simple mathematics, as average energy as h nu exponential minus h nu by kT plus 2 h nu exponential minus 2 h nu by kT plus so on and so forth, 1 plus exponential minus h nu by kT plus exponential minus 2 h nu by kT plus so on and so forth. We have simplified this to obtain the average energy h nu by exponential h nu upon kT minus 1, and we have said that the principle of equipartition of energy does not hold good in microscopic world, since we know the number of oscillators between the frequency range nu and nu plus d nu as 8 pi square d nu upon c cube. We have written the energy density in a black body as E nu is equal to 8 pi h nu square upon c cube into 1 over exponential h nu upon kT minus 1. We have expressed this expression in terms of wavelength by using c is equal to nu lambda, and we have written E lambda as 8 pi hc upon lambda power 5 into 1 over exponential hc by lambda kt minus 1. We have said these two expressions are called as Planck's radiation laws, and the second expression can completely fit into the blackbody radiation spectrum. Hence we said that the Max Planck's revolutionary postulate, that is the energies are quantized, has revolutionized the modern physics. Thank you.